Hi, welcome to an academy. I'm welcoming you all to India's online largest online learning platform, an academy. Now we are happy to announce that we are going to providing the training to students who are appearing for GATE and service examinations, engineering service examinations. About myself, I G Venkatrao. I have 16 plus years of teaching experience. So far, I mentored more than 60,000 students for their GATE examination. At present, I am pursuing PhD from JNTU Kakinada. My specialization is in VLSA domain. Now, first we check how to get the Unacademy Learning app. If this app is in your device, it's okay. Otherwise, install it. Now, just go to Play Store in your device. There type Unacademy. Okay, once you type it, then you get the Unacademy Learning app like this with this symbol. Okay, now just click on this install button. By clicking on this install button, it will install the Unacademy Learning app into your device. And once you open that Unacademy Learning app in your device, it will shows what are the different courses available in that, and in each course different subjects and their respective faculty who are the top educators handling those subjects. You will get that information. And at the same time, if you wish, you can see their brief profile, brief introduction about the faculty or educators, top educators who are going to handling their subjects. Okay, here I am showing some of the top educators to you. Tiwari sir, he is a IIT topper, and Ankit Goyal, he is the two times All India topper in GATE electrical display. And Jain sir, he is the top faculty from computer science and engineering. And Jaspal Singh sir, he is the ex-IAS officer, All India 4th rank he got. Okay, now here you can observe few more top faculty, okay, in different disciplines. Now we are happy to announce that recently we started two new batches, one for GATE 2023 and another one is for GATE 2022, okay, in different disciplines. In mechanical engineering, there is a Ascend batch for GATE 2023. This batch started from 8th February. Here are the top faculty I am showing here. They are going to handling the subjects for the mechanical engineering. And again there is a eval batch for GATE 2022, again mechanical engineering. See, just before I told you now, one for GATE 2022, other one is for GATE 2023. Okay, so this batch also started from 8th February 2021. And don't forget to use my code during subscription to get 10% discount. VRAW10. Don't forget to use my code. Next, there is a Ascend batch for GATE 2023. This time this is civil engineering. Here are the top faculty who are handling the courses here, and this batch is started from 8th February. Okay, this is for GATE 2023. Next we have a eval batch for GATE 2022. Okay, this is for civil engineering, and this batch started from 8th February 2021. Sorry. And there is a eval batch for GATE 2022. This is for computer science and information technology. This batch started from 8th February, and these are the top faculty who are handling the subjects in computer science and engineering. Okay, now there is a Ascend batch for GATE 2023 electrical engineering. Okay, this batch started from 1st February. Okay, here are the top faculty who are handling the subjects in that. Okay, And don't forget to use my code VRAW10 during subscription. By using this code VRAW10 during subscription, you get 10% discount. You get 10% discount. Now there is a Ascend batch for GATE 2023. This time this is for Electronics and Communication Engineering, EC department. This batch started from 1st February. And next there is a Evolve batch for GATE 2022. This is for Electrical Engineering. This batch started from 1st February 2021. Okay. And there is a Evolve batch for GATE 2022. This time this is for Electronics and Communication Engineering again. Now here are the top faculty who are handling the subjects in this. This batch started from 1st February 2021. And there is a Evolve batch for GATE 2022 for Chemical Engineering. So if any of your friends are having chemical engineering background, please inform them there is a batch started in Unacademy for GATE training. Okay, don't forget. So by using this code VRAW10 during subscription, you get 10% discount. And this batch started from 25th January 2021. Okay. Now here are the different disciplines who are available in Unacademy: mechanical engineering, electrical engineering, civil engineering, production and industrial, instrumentation engineering, computer science and IT departments, chemical engineering, electronics and communication engineering. Okay, these are the different engineering disciplines available. Next, we move to subscriptions. There are two types of subscriptions. One is a plus subscription. This is the basic plan. Second one is the iconic subscription. Okay, iconic subscription. So it will take your preparation of GATE and engineering service to the next level with personal coach. We will provide a personal coach to you here. Okay, now there are few commonalities. Your classes are taken care by the India's best educators, and there are interactive live classes, structured courses and PDFs. Now live tests and quizzes. Here also live tests and quizzes. But now here is the important. Once you've written some test or you attempted some quiz, okay, now your analysis, your answer sheet is going to be analyzed by the expert. Okay, and based on that analysis, they will give where you are going to be strong and where you need more preparation. Okay, where you are committing mistakes, they will prepare that one. Okay, based on that, they will prepare proper study planner to you, and they will provide a study material to you. By following these two effectively, any student can success in their competitive exams. That is the intention behind to place a personal coach. For each and every student, there is a personal coach. For each and every student, there is a personal coach. Don't forget. Okay, now we check the cost for each and every subscription. Now for plus subscription, there are different subscriptions are available in plus plan. 1 month subscription, 3 month subscription, 6 month subscription, 1 year, 18 months and 24 months. As a faculty, I will recommend this one, minimum 1 year subscription. Then only you will understand subject thoroughly. Then only you can complete your preparation, you can revision the multiple times all the subjects, and you can attempt more number of exams before going to final examination. Okay, now you have a proper time to analyze where you are strong, where you need more preparation, where you are committing mistakes. Okay, you get some time. That is the reason to suggest to the students to take minimum 1 year subscription. Okay, and if you don't have much time, and then you can go for remaining also, no problem. And the beauty here is you get the EMI option facility also available to you. No cost EMI option also available to you. Okay, now Here, by using my code VROW10 during subscription, you get 10% discount. After 10% discount, it became 27,225 rupees only. 27,225 rupees only. Okay. Now, I'm going to next Iconic plan. In Iconic plan, only two subscriptions, 1 year subscription and 2 year subscription. In 1 year subscription, its cost is 50,250 rupees, and there is a EMI option also is that 400,188. And by using my code during subscription VROW10, you get it by 10% discount. 10% discount. Now the discount is, after discount it became 45,225 rupees. 45,225 rupees. Okay. Now the reason here to charge this much is we are providing a personal coach. That personal coach is allotted to you. For each and every student we are allotting one personal coach. That personal coach is going to taken care by complete your academics, your subjects. Okay. Now if you compare the cost of this one and previous plus plan, the plus plan amount what you are spending for this is more or less close to the amount what you need to spend if you join somewhere at outside for training, a training. You need to travel from your home to that location throughout the year during weekends, in weekends as well as during public holidays. At that time you need to go for traveling. For the traveling, whatever the amount you need to spend, more or less that is close to that amount. And this amount is the amount what you are paying at tuition fee, as a tuition fee to institute. But here you get more benefits compared to that. Here you are getting more benefits. Okay, similar to that we are conducting online examinations, and moreover your paper is analyzed by the expert and they will prepare a note where you are strong, where you are need a more preparation, okay, where you are committing mistakes, and we will notify you each and every point to you, and we will correct those gaps where you are doing mistakes. We will fulfill those gaps. We will fulfill those gaps. Once we will fulfill those gaps, then you can easily attempt the GATE exam, and you can definitely you get the success in that examination. So my dear students, don't waste your time. Join this one today itself, okay, and get success in your career. Thank you. Now we are moving to our session, that is problems on PN junction diode. Sorry, just before session we completed a few problems. Now I am going to the next problems. Yeah, yes, see this. So this is the problem. Use the given data for questions 13 to 16. So here 13 and 14 is there. So next slide we get the 14 and 15 and 16 problems. Okay, now I am going to this. For a gallium arsenide PN junction, the following information is available. DE means denser, density, diffusion coefficient of electrons 205 centimeter square per second, and diffusion coefficient of holes is 9.8 centimeter square per second. Electron lifetime is 5 into 10 power minus 8 seconds, and whole lifetime is 10 power minus 8 seconds. The value given are for minority carriers, electrons on the p side and holes on the n side. Okay, doping concentrations, Na they given and Nd they given. Okay, and take temperature to be 300 Kelvin and Ni value 1.8 into 10 power 6 per centimeter cube for gallium arsenide. So the first part in this is, what is the built-in potential of the junction at equilibrium? Give your answer in volts. So now I am going to giving the solution to the 13th problem. So built-in potential is nothing but a contact potential. Its value is Vt into ln of Na Nd by Ni square. Ni square. This is the problem. They given Na, Nd and Ni. Just to substitute. Next Vt, we know that it is 25 milli electron volts. Sorry, millivolts, 0.025 approximately, or 26 you can take, not much difference, into ln of NaNd. Na value is 5 into 10 power 16 into Nd is 10 power 16 by Ni square 1.8 into 10 power 6 into 1.8 into 10 power 6. Okay, because it is Ni square. So now it is now its value is 0.025 into ln of 10 power 16, 10 power 16, 10 power 22 by 10 power 12. It is 10 power 10. Okay, next 5 divided by 1.8 divided by 1.8, that is 1.54. 1.54 into 10 power 10. Now it is 0.025 into ln of 1.54 plus 10 into ln of 10. Ln of 10, we know that it is okay, take ln of 10 this time. Ln of 10. So ln of 1.54, its value is 0.43. So 0.025 into 0.43 plus 10 into ln of 10 is 2.3, 302. Now it is 23 plus this one, 23.43. 23.43 into 0.025, that is 0.585 electron, 0.585 volts. 0.585 volts. That is the answer for 13th one. So 0.585, approximate value is 0.6. So you can make it approximately 0.6 volts. So this is the option A for this. Next one is, what is the total diffusion length of minority carriers holes on the n side? So they want the diffusion length on minority carriers holes. So diffusion length of holes is square root of dp into tau p. So they given dp value and tau p value to you. So the given dp value is dh 9.8 into tau p is tau h, it is a 10 power minus 8, 10 power minus 8. So square root of 9.8, 9.8, it is a 3.13, 3.13 into 10 power minus 4 centimeters. So they want in micrometers. So 10 power minus 4 can be written as 1 micrometer. So 3.13 micrometer. This is the answer for 14th one. 3.13. So this is the approximate value. 3.13. 3.1. Okay. So that is the problem. Sorry. Now, like this, you can solve the problem. Now I'm moving to next one. Yeah. So same data. Now calculate the total current in the PN junction diode for a forward bias of 1 volt. See here they are applying a forward bias of 1 volt. If the junction cross sectional area also they given 10 power minus 3 centimeter square, and they want answer in terms of the order of milliamps. Okay, now I'm going to the 15th question answer. Okay, just a minute, sir. Now see this. So they want the diode current. So we know the current equation. ID equals to I naught into e power Vd by eta Vt minus 1. Okay, default in general we are taking eta is 1. Okay, take eta is 1, no problem. Vt we know that. Vd they given it as 1 volt. 1 volt. 1 volt. Next Vd. Okay, now we need I naught value. Okay, so I naught value. So there is a equation for I naught. I naught is, we derived an equation for this, that is A into Q into, okay, dP by LP, sorry, here into Ni. Okay, I will take this Ni before. A into Q into Ni square into dP by LP into Nd, okay, plus dN by Ln into Na. This is the equation for I naught. But they given dn, okay, but L value they did not given. Now already we calculated. Now I am writing everything in terms of d and tau. Now another form we have. That means just I am replacing L by root dP into tau p. Now it is A into Q into Ni square into 1 by Nd into, you get square root of dP by tau p plus 1 by Na into square root of dN by tau n. Just substitute the values. Therefore I naught is area. The given area is 10 power minus 3 centimeter square. Okay, 10 power minus 3. Q 1.6 into 10 power minus 19. Okay, next into Ni square. Ni square. Ni is 1.8 into 10 power 6. So 1.8 into 10 power 6 into 1.8 into 10 power 6. Fine. Next 1 by Nd. So Nd value they given it as 10 power 16. So 1 by Nd, 1 by 10 power 16 into square root of dP by tau p. dP is 9.8 by tau p is tau h 10 power minus 8. 10 power minus 8 plus 1 by Na. 1 by Na. Na is 5 into 10 power 16. 5 into 10 power 16 into square root dn 205 by tau n. 5 into 10 power minus 8. 205 by 5 into 10 power minus 8. So this is the data. You need to simplify this. Yeah, 10 power minus 8. Fine. So simplify this. Then you get ID. Therefore ID is, see this, sir. Now this is 6, 612. Now it became 10 power minus 7. Now taking this one outside, it became 10 power minus 4. It is also 10 power minus 4, and 10 power 16 I am taking common. Now it became 1 by 10 power 16 into 1 by 10 power minus 4. And after that it became 10 power 12. 10 power 12. Now it is 10 power 12. Fine. So 10 power minus it is, don't disturb that. Now it is 10 power minus 7 minus the 10 power minus 10. Okay. Now minus 4. So 10 power 12. Okay, fine. So area and Q Ni square. Fine. Now it is 10 power minus 12 minus 15 minus 22. 10 power minus 22. 22 into 1.6 into 1.8. 1.6 into 1.8 into 1.8. That is 5.184 into square root of 9.8. That is 3.13 plus square root of 205 by 5. So 205 divided by 5, that is a square root, that is 6.4 divided by 5, that is 1.28. 1.28. Okay. Next. So this is the data. Minus 3. Okay. 1.8 into 10 power minus 8. Now I am checking just values. We taken correct values or not. Okay, fine. Now this is 10 power minus 3, 10 power 19, 6, 6, 12, 10 power minus 7, 10 power minus 10. Okay, now it is 10 power minus 4, 10 power minus 4, dp by lp into na. Ni square pnp. So here we have, that is the equation, a into q into dp by lp into pn naught. Pn naught value is ni square by nd. So okay, we taking correct one. Now just simplify this. 1.28 plus 3.13 is equal to this much into 5.184. 22.86. So 22.86 into 10 power minus 22. That's I'm thinking about the values. It is square root of dp. Okay, just we check it later. Now I'm going to this side. Now therefore id is I naught 22.86 into 10 power minus 22 into e power vd value is 1 volt by eta 1 vt value. Vt is 25 milli, so that means 1000 by 25. 1000 by 25 minus 1. So that is e power 40. E power 40. E power 40. It is 2.35 into 10 power 17. So 22.86 into 10 power minus 22 into, it is 2.35 into 10 power 17. Okay, minus 1 not valid compared to this. Now it is 2.35 into 22.86. 0.86, that is 53.72. 53.72 into 10 power minus 5 amperes. They want of the order of milliamperes. They want of the order of milliamperes. Okay, just go to that. Now it is 10 power 5 amperes. You want milli, 10 power minus 3, it is 0.53 milliamps. Now 0.5, so not that. So you can add one more because we verified everything. It is 0.5 approximately. Okay, so that is the answer. VD we applied 1 volt by point. VT is 25 milli, so take that milli, it became 1000 by 25. Okay, and nothing, everything is clear. Next, calculate the change in diode voltage. Next problem, calculate the change in diode voltage from 1 volt to 1 volt that will cause an increase in the diode current by 100 times. Calculate the change in diode voltage. That means by how much change in diode voltage will increase the diode current by 100 times. Okay, see here they are going to comparing only the ID value and VD value. Okay, so that means they are going to, we got ID by applying ID with VD. So our relation we have, ID is directly proportional to e power VD by VT. Okay, eta take it 1. This is ID1, VD1. Now second case, I am taking ID2, the ID, just a minute sir. From this we can write directly ID1 by ID2 equals to ED1 by VT by ED1 by, sorry, ED2 by VT. Now it became e power VD1 by, sorry, VD1 minus VD2 by VT. We know it. Now what they are saying, diode current is increased by 100 times. That means they given ID2 is 100 times ID1. Okay, so substitute that one here. Now it is from this ID1 by 100 times ID1 equals to e power VD1 minus VD2 by VT. Leave it. Now these two gets cancelled. 1 by 100. Okay, now we can take like this one, like this. 100 equals to e power VD2 minus VD1 by VT. I am taking like this. Take natural log on both sides. It is ln of 100. Ln of 100 is 4.6. Ln of 100 equals to VD2 minus VD1 by VT. Okay, this is 10 square. Now it is 2 into ln of 10 is 2.3. 4.6 is equals to VD2 minus VD1 by VD1. Sorry, VT. Now, so that is 4.6 into 0.025. That is 0.025 Therefore change in applied voltage VD2 minus VD1 is 0.115 volts. 115 volts. Now just check the options. 0.115. So 0.115 volts. So 0.115 means, see, 0.115 volts we get. So 115 millivolts. So closest value is not 1 milli, not 30 milli, not 60. This is 120 millivolts. 120 millivolts. Okay. So because that is a 4.6 into 0.026. Yeah, that is 1196. 1196. This is by taking, now this is 119.6 volts, 6 millivolts. Here just I take, previous case I take VT value 25 milli. Now I am taking 26 milli. By taking 26 milli, it became 119.6. So it is 120 millivolts. Okay, sir. Clear? Here also we get a variation. In 15th also we get a variation because of that problem in that one, that VT value variation. Okay. Anyway, procedure is the same. Now this is the 16th problem. Now I am moving to the next one. Already we solved this. Now say this problem. The IV characteristics of three types diodes at the room temperature, made of semiconductors X, Y and Z, are shown in figure. Okay, these three are made by different semiconductors X, Y, Z. Assume that the diodes are uniformly doped and identical in all respects except their materials. Diodes are uniformly doped, identical in all respects. If the energy gaps are Eg of X, Eg of Y and Eg of Z are the band gaps of X, Y and Z respectively, then you need to relate the energy gaps of that material. See, if more energy gap is there, now you need to apply more threshold voltage to get the conduction. So here if you observe, this is the threshold voltage of X material diode, this is the threshold voltage of Y material diode, and this is the threshold voltage of Z material diode. That means EGZ is more compared to all. Therefore EGZ is more compared to all. Next EGY and next EGX. So this is the problem solution. So EGX greater than EGY greater than EGX. So EGX less than EGY less than EGZ. Both are same. Now option is C for this. Sorry. Next. In a PN junction diode at equilibrium, which one of the following statement is not true? That means you need to identify the false statement. You need to identify false statement. See, the hole and electron diffusion current components are in same direction. The hole and electron drift current components are in same direction. On an average, holes and electrons drift in opposite direction. On an average, electrons drift and hole diffuse in the same direction. Okay, this is related to current components. Now I am going to representing that current components of a diode once again. So let us take, this is the junction and this is the P region and N region. Now from this, holes are diffusing this side and hole current, they given hole current as well as hole diffusion, electrons and holes. See, this is the direction of, in forward bias it became positive and it became negative. Now holes are diffusing this side, hole movement as well as current. This is the drift current, hole drift current, hole drift movement as well as hole drift current, and this is the electron drift movement, electron drift, and electron diffusion, electron diffusion, and this is the hole diffusion, hole diffusion. Now I am writing the current equations. See currents. This is the hole current, hole drift current. I capital DP, hole drift current. This is the hole diffusion current, I small d P. And electron is moving this side and its current is opposite direction. This side. This is going to be I, okay, drift by electron, and electron is moving this side. Now current should be opposite. Now this is the current by I diffusion by M. Now see this, the hole and electron diffusion current components, first they want current components are in same direction, electron and hole diffusion currents. See this, electron diffusion current, this one, okay, and hole diffusion current, hole diffusion current, both are moving in the same direction, both are moving from P to N. So first one is a true statement, true statement. Second, the hole and electron drift current components are in same direction. See, hole drift current is from P to N, electron drift current also from P to N, current direction just they want. So both are same direction. This is also a true statement. And next, on an average, holes and electrons drift in opposite direction. See, holes and electrons drift in opposite direction. Holes are drifting from P to N, electrons are drifting from N to P. So opposite direction. This is also true statement. Next, on an average, electrons drift and holes diffuse in the same direction. See, electrons are diffusing in this region away from the junction towards P side, and electrons are diffusing away from the junction towards N side. Both are opposite side, they are diffusing like this. So but they given same direction. This is the false statement, false statement. So this is the option. Okay, so option is the D is the correct option, but that is the true statement, that is the false statement. Remaining all are the true statements. Here they design the question based on the diode current components. Okay, now I'm moving to next problem. See, a step graded diode with a contact potential 0.65 volts has a depletion width of 1 micrometer at equilibrium, and the forward voltage at which this width reduces to 0.6 micrometer. So their plan is to take the forward bias of the diode, but some depletion region width should exist. That is the condition. Okay, now they given the contact potential 0.65, fine, 0.65 volts, and depletion width under open circuit, under equilibrium they said clearly it is 1 micrometer. Okay sir. And the forward voltage at which this width reduces to 0.6 micrometer. Now what is the width? I want the width of 0.6 micrometer. At which forward voltage this is happened? What is the voltage for diode? That means that is the forward voltage to get this value. See, in forward bias we have an equation for depletion region width, that is in forward bias depletion width is square root of 2 epsilon by q into 1 by Na plus 1 by Nd into V0 minus applied forward voltage Vf, applied forward voltage Vf. Now in this I am going to taking V0 common, therefore depletion width W is square root of 2 epsilon by q into 1 by Na plus 1 by Nd into V naught taking common into 1 minus Vf by V naught. Okay. Now, and W is written as this part became, see, this portion is nothing but a W naught. So, which is W naught into square root of 1 minus Vf by V naught. Vf by V naught whole power 1 by 2. That is the option. Now, just substitute the values. Everything they given. W value is 0.6 micrometer. So 0.6 micrometer. W naught 1 micrometer. 1 minus forward voltage you need to calculate by contact voltage 0.65. Here whole power 1 by 2. Now this is 0.6. 0.6 square equals to 1 minus Vf by 0.65. Okay, now it is 0.36. Now Vf equals to 0.65 into 0.65 into 1 minus 0.36. Okay, so now it is 0.65 into its value is 0.64. That is the forward voltage required. 0.64 into 0.65, that is 0.416. 0.416. Sorry. So that is the voltage required. A forward voltage of this much required to reduce the depletion width from 1 micrometer to 0.6 micrometer in forward bias. Okay, that is the. And so far we are expecting depletion width they concentrate only on reverse bias, but in this case you observed they concentrated the depletion region width in forward bias also. Okay, so my dear students, please be concentrate on the concepts, not on the formulas. Okay, so next one is, go to next problem. See, now the resistivity of germanium p-n junction diode. See, now they are going to concentrating on semiconductor part resistivity. Okay, see, the resistivity of germanium p-n junction diode is 2 ohm to centimeter on p side and 1 ohm to centimeter on n side. Calculate the built-in potential. Ni value 2.5 into 10 power 13 per centimeter cube. Mobility of holes 800 and electrons 3820 meter square per volt to second. See, resistivity is 1 by conductivity. We know that. They given on p side 2 ohms. That means sigma p, rho p is 2 ohms. So its value is 1 by Na into Q into mu P. It is, they given it as 2. Similarly, they given N is 1 by sigma N, O-N, which is 1 by Nd into Q into mu N. So that is, they given it as 1. Now get the Na and Nd from this. Now I am writing Na from this. Na is 1 by 2 into Q, 1.6 into 10 power minus 19 coulombs into mu P, whole mobility is 800. Similarly here, Nd is 1 by 1 into Q, 1.6 into 10 power minus 19 coulombs into mu N, 3800. Just simplify this. So 0.2 into 8, 25.6. 1 divided by 25.6 point, it is a 0.039 into 10 power 17, or 3.9 into 10 power 15 per centimeter cube. That is the value of Na. Similarly, here I am going to Nd value, that is 1 divided by 1.6 divided by 38, that is 0.0164 into 10 power 17 per centimeter cube, or 1.64 into 10 power 15 per centimeter cube. That is the Na and Nd. They given already Na, Ni. Now we go for contact potential. So we got Na and Nd. They given Ni. So Na is 3.9 into 10 power 15, 3.9 into 10 power 15 per centimeter cube, and Nd is 1.64 into 10 power 15 per centimeter cube, and Ni is 2.5 into 10 power 13, 2.5 into 10 power 13 per centimeter cube. Now I am going to equation contact potential. Our contact potential equation is Vt into Ln of NaNd by Ni square. So Vt is, V0 is Vt 25 milli, 0.025 into Ln of Na 3.9 into 10 power 15 into Nd 1.64 into 10 power 15 by Ni square 2.5 into 10 power 13 into 2.5 into 10 power 13. That's it. Now simply use to cancel this and it became 100. It is also 100. Okay, it is a 390, it is 164. 390 into 164. 390 into 164 is divided by 2.5. Divided by 2.5 again. Now it is a 10,233.6. So we need ln of that. That is 9.23 into 0.025. It is 0.23 volts. 0.23 volts. That is the V0. Okay. Okay, sir. So like this you calculate the values. They given some data. The data is to calculate, to extract the whatever the parameters we need. Okay, we use that data for that purpose. Now I'm going to next problem. Now find the barrier capacitance in picofarads. Barrier capacitance. So we are in reverse bias, sir. Barrier capacitance in reverse bias of a germanium PN junction whose area is 1 mm by 1 mm. Okay, and whose space thickness is 2 into 10 power minus 4 centimeter. if the dielectric constant of germanium is 16 relative to free space. Find the barrier capacitance. Okay, now junction, the given junction area 1 mm by 1 mm. Okay. Sorry, it is 10 power minus 3. See, 1 mm is in centimeters, 1 into milli 10 power minus 3 into meters and square centimeters. Now it is 10 power minus 1 centimeter. Now it is 10 power minus 1 into 10 power minus 1, 10 power minus 2 centimeter square, that is the area. And whose space charge thickness, that means a depletion region width they given. Okay, depletion region width they given 2 into 10 power minus 4. Okay, minus 4 centimeters. If the dielectric constant they given, okay, fine. Next, they want barrier capacitance. Okay, now the barrier capacitance, a junction capacitance or barrier capacitance is, we know that epsilon A by D means oxide thickness, space charge thickness. Now epsilon we can write epsilon naught into epsilon R into area by W naught. Epsilon naught, they we know the epsilon naught value 8.854 into 10 power minus 14 farad per centimeter. 10 power minus 14 farad per centimeter into epsilon R, relative value they given, it is 16 into its area. Area is 10 power minus 2 centimeter square by W naught, 2 into 10 power minus 4. Just simplify this. So it is 10 power minus 10, 10 power minus 4 cancel. Now it is 8 times. Okay, 8.854 into 8, 10 to 10 power minus 12. So 8.854 into 8, that is 70.8 into 10 power minus 12 farads. 10 power minus 12 is pico, so 70.83 picofarads. That is the answer. Okay, 70.83 picofarads. Now I am moving to next problem. In uniformly doped abrupt p-n junction, the doping level of the n side is 4 times the doping level of the p side. The ratio of depletion layer width is, see this. In a uniformly doped abrupt p-n junction, the doping level of n side, nd, is 4 times the doping level of p side, nj. Then the ratio of depletion layer width is, so first they talk about n side, that's why depletion layer ratio also you need to take xn naught by xp naught, what it is, how much it is. So we know one relation, that is NA into xp naught equals to ND into xn naught. Already we derived this one in previous sessions. From this, xn naught by xn xp naught equals to Na by Nd. That's it. Na value, Na as usual I am taking, by Nd they given it as 4 times Na. 4 times Na. Both will cancel. Now it is 1 by 4. 0.25. That's it. So this is the option 0.25. Okay. Next. Simple problems are there is. Next. In an abrupt PN junction, the doping concentrations on P side and N side are Na 9 into 10 power 16 per centimeter cube and Nd is 2.7 into 10 power 17 per centimeter cube respectively. The PN junction is reverse bias and the total depletion width is 3 micrometer. Clearly they mention, sir, it is reverse bias. So and depletion width is 3 micrometer. The depletion width on P side is how much? They want to depletion width on P side is how much? Okay. They given Na and Nd also to you. We have a relation for xp. Now xp is already we derived this one, sir. W into Nd doping on opposite side by Na plus Nd. Just to substitute values. Simple. Depletion they given 3 micrometer into Nd value 9 in 2.7 into 10 power 17 by 2.7 into 10 power 17 plus Nj 9 into 10 power 16. Just simplify this. Three micrometer into, so I am writing this is 27 into 10 power 16. Here also 27 into 10 power 16 plus 9 into 10 power 16. 27 plus 9, 36 into 10 power 16. Now simplify this. This 16 gets cancelled. Okay. 9 3 times. 9 4 times. Okay. So 9 by 4 micrometers. So 9 by 4 is 2.10 2.25 micrometer. 2.25 micrometer. Yeah, this one. Depletion width on P side it is. Okay, now let us take it is the junction and depletion width on P side is, total depletion width is 3 micro. In that it is 2.27 this side. This is 2.25 and this is just 0.75. And doping on Na is 9 into 10 power 16. Doping on P side, doping on P side is 9 into 10 power 16. Doping on N side is 2.7 into 10 power 17. See, compared to this, it is more doped. Okay, even 10 times doped. That's why depletion width is extended less this side compared to this side. So from this, we can conclude depletion width is always extended more towards lightly doped region. Okay, already we discussed that one also. So this is very, very important, sir. You may get this one in theoretical part also. Okay. Now I am moving to next one. Yeah. See this? So semiconductor devices often contain high-low junctions for which the doping density changes magnitude but not sign. The below figure shows the such a high-low step junction. ND1, ND2 they given. Calculate the built-in potential of the above high-low junction. See, don't no need to confuse anything here. Simple. Here they given, instead of taking p side and n side and giving NA this side and giving ND this side, simply they taken the simple semiconductor and this side they doped with ND1 amount, they doped with ND2 amount. Now there is a change in concentration. This time it is, this side is 10 power 18 and this time this side this is 10 power 15. Okay, now just go to equation. Now our contact potential V naught equals to Vt into Ln of Na Nd by Ni square. Now it became Nd1 into Nd2 by Ni square. That's it. That's it. Nd1, Nd2 they given, substitute, but Ni was missed in this problem. Okay, just if they give some Ni, just they give definitely Ni, take that value and substitute here Ni. Substitute your Ni value also here, then you get the contact potential. Okay, next session I will get that Ni, because here they did not mention which type of semiconductor it is. Because of that I am unable to give the Ni value properly. Okay, I will cross verify this problem once again. Next problem. An ideal PN junction diode is forward biased moderately. First of all, it is forward biased moderately such that the applied bias is much greater than the thermal voltage. Applied forward voltage is much greater than the thermal voltage Vt. How much voltage is needed to increase the diode current by a factor of 10? How much voltage is needed, okay, needed to increase the diode current by a factor of 10? Okay, just a minute, I am going back. There we derived one equation. Yeah, see this, id1 by id2 is, we applied this. Okay, now id2 by id1 is e power vd1 minus, okay, id2 by id1 is e power vd2 minus vd1 by vt. Now I am going to using this expression directly. Yeah, so we know that id is directly proportional to e power vd by vt. Now we can write id2 by id1 is e power vd2 by vt by e power vd2 d1, sorry, d1 by vt. This is e power vd2 minus vd1 by vt. Now they given, this is id1, see, increase the diode current by factor of 10. That means id2 is 10 times id1. Okay, just substitute this. It is 10 times id1 by id1 equals to e power vd2 minus vd1 by vt. Now this is 10, taking the natural log on both sides. Now vd2 minus vd1 equals to vt times ln of 10. ln of 10 is 2.3, vt 0.025 into 2.3 volts. That's it. 2.3 into 0.025, that is 0.0575. Okay, take 2.6, 0.3 into 0.026, 0. So I'm taking this is 6, sir, 0.026, 26 millivolts. Then it is 0.0598, okay, volts. So in milli it is a 59.8 millivolts. Now the approximate value is 60 millivolts. Approximate value is 60 millivolts. Okay. So I'm moving to next problem. See here, a P plus N junction has a built-in potential of 0.8. Built-in potential, sir, that means a V0, 0.8 volts. The depletion layer width at a reverse bias of 1.2 volts is, depletion width equals to 1.2 volts at a reverse voltage of 1.2 volts. Sorry, reverse voltage of 1.2, depletion width is 2 micro. 2 micrometer. 2 micrometer. Now, for a reverse bias of 7.2 volts, if the reverse voltage is 7.2 volts, let us take it is 1. What is the depletion layer width? Now, what is the depletion layer width? Now, I am taking this is a W1, W2. We have an equation for this. Our equation for depletion region width W in reverse bias is square root of 2 epsilon by Q into 1 by NA plus 1 by ND into V0 plus reverse voltage VR. From this we can write all are constants because same diode. W directly proportional to square root of V0 plus VR. Now we can write from this W1 by W2 equals to square root of V0 plus VR1 by square root of V0 plus VR2. Just substitute the values. W1 value 2 micrometer, 2 micrometer by W2 you need to measure square root of V0 they given 0.8 plus VR1 1.2 volts by square root V0 0.8 plus reverse voltage second time 7.2. So this is root 4 by 8, square root of 4 by square root of 8. Okay, so which is 1 by root 2. That is 2 micrometer by W2. Okay. Okay, sir. Now 1 by root 2. So therefore W2 can be written as 2 micrometer by 2 micrometer into root 2. 2 micrometer into root 2 because it has to be increased. So root 2 into 2 micro, that is a 2.8 micrometer. Just a minute, sir. Built-in potential 0.8. Okay. W1 1.2 volts they are applying for W1. Okay. 2 micro. Fine. 2 micro. I will cross check just a minute, sir. 2 micro 0.8 1.2. Okay. Now it is 2. Sorry, it is 2, sir. Sorry, it is 2. 2 by root 2 by root 8. It is 1 by 2 because 1 by root 4, that 1 by root 4 is 2. So it is 2. Now it is 4 micrometer. Sorry, that is 4 micrometer. So this is the option 4 micrometer. Okay. Next one. silicon PN junction diode under reverse bias. So it is in reverse bias, fine. Has a depletion region width of 10 micrometer. So depletion region width in reverse bias is 10 micrometer. The relative permittivity of silicon is 11.7 and permittivity of free space 8.85 into 10 power minus 12 farad per meter. See here they try to give the epsilon value. We know the epsilon value already, 1 into 10 power minus 12 farad per centimeter by multiplying those two, approximate. The depletion capacitance of the diode per square meter area. Junction capacitance or depletion capacitance per square meter area. Per square meter area. Okay. Now we have an equation for junction capacitance, that is epsilon A by D. So here D nothing but a depletion region. Okay. So per square meter they are asking. So everything should be of the order of meters. Now it is already in meters. Now I am writing this is 10 into 10 power minus 6 meters. And it is 10 power minus 12 by 10 power minus 2. It is 10 power minus 10 meters. Yeah, substituting. It is 10 power minus 10 into, sorry, we need by Cj by A here. Therefore, Cj by area per unit area. Epsilon is 10 power minus 10 meters by, it is 10 power minus 5. 10 power minus 5. Okay. Epsilon A by D. So this is a 10 micrometer. Fine. 10 micrometer. 10 power minus 6 meters. Epsilon is 10 power minus 10. Now it is 10 power minus 5 per meter square. Farad per meter square. Farads. 10 power minus 5 farads per meter square. Per meter square. Okay, but they given of the order of microfarads. Now see the meaning of this one is in micro. So 10 power 6. Now it is 10 microfarad per meter square. Already they given per meter square here. Okay, that's why they did not mention square meter here. So this is simply 10 microfarads. So 10 microfarads is the answer. This is the answer, 10 microfarads. Okay. Like this, students, don't confuse. Okay, just pick the point where you want exactly. Okay, and solve that. Now I am going to another one. See, consider an abrupt PN junction. Let VBI be the built-in potential of the junction, built-in potential of the junction, and VR be the applied reverse bias. If the junction capacitance Cj is 1 picofarad, for VBI plus VR is 1 volt. And one more thing, sir, we know that depletion width is directly proportional to V0 plus VR. Already we know that. Here they mentioned V0 is nothing but a built-in potential, sir. Built-in potential. So I am writing according to that. VBI plus VR. In terms of capacitance, Cj is inversely proportional to square root of VBI plus VR. We know that. Okay. Now, for value of VBI plus VR 1 volt, it is 1 pico, and for VBI plus VR equal to 4 volts, what is the Cj, junction capacitance? Now I am writing the expression for this. See, Cj1 by Cj2 equals to square root of VBI plus VR 2 by VBI plus VR 1. Okay, now substituting the values. They given it is 1 picofarad 1. Now we need to calculate Cj2 equals to square root. It is 4, 2 value by 1. It is 2. Now they given in picofarads. Therefore, Cj2 is 1 by 2 picofarads. That is 0.5 picofarads. Okay, 1 by 2 or 0.5 picofarads. So that is the value of junction capacitance. Okay, my dear students, thanks for spending your valuable time with us. So next session we go to the remaining problems. We have more problems. Next session we go and discuss the remaining problems. And thanks for spending your valuable time with us. Don't forget to use my code VRAO10 during subscription, and don't forget to subscribe, and please hit the bell icon to get the notifications. Okay, and join our Telegram group for latest updates on our upcoming videos, and please give your valuable comments to us. It is going to be boost to us. Okay, and don't waste your time. Join an academy as early as possible and continue your learning process. Okay, and good night. Thanks for spending your valuable time with us. Once again, I'm welcoming you all to an academy, India's largest online learning platform. Thank you.